As an example of linear algebra application, I want to talk about image transforms. And also I will talk about application of determinants to image transforms. There is a multitude of various image transforms available, but we will discuss only a few of those. Generally speaking, image transform, which is also called parametric global warping, is a coordinate changing machine. It takes some pixel, like that red pixel here for example, and transform it into some other location on the image. And you apply exactly the same thing to all of the pixels of the image. Now, this is why it's called global, because it's the same for any point P that you have in the image, and can be described only in a few parameters. Parameters are just some numbers of the problem. So every pixel will be converted into some other pixel, and other pixels will be converted exactly by the same equation, exactly by the same transform. This is image transformation. A simple example of that, it could be image rotation, image scaling, and so on. As I said, many transforms are available, but we will concentrate only on a few. First is image translation, where all pixels in the image are just translated or moved in one direction. So if you have original image like that, square, it will be just translated like that and moved to some other place. Another one is a rotation. Rotation, you're using exactly the same square, and then you're rotating that square like that. This transform is also called Euclidean transform, and could be just any angle, and Euclidean transform includes rotation and translation together. Scaling is another one, where you're just changing the size of the image in X direction and changing the scale in Y direction. Now, similarity transform includes both Euclidean and also scaling. So if you rotating, moving, and scaling together, this transform is called similarity transform. More general transform is affine transform. It also includes additional sharing of the sides, so you're kind of squeezing it and you get a little bit different shape. And even more broader transform that we will not talk about is projective transform, which could also have some sort of perspective in the changing of the image view. So it can have like moving into third dimension of the picture, going into depths. So this is projective transform. But we will be discussing only translation, rotation, scaling, and affine transforms. Let's start with the definition of the translation. Let's say you have image I. In that image you have pixels, and pixels are picture elements or points, and each point will have its own coordinate. So for all coordinates x and y, which belong to that image I, the translation by a vector AB, which means this is some sort of vector by which you want to move that image. So every pixel will be the following. New pixels will say with the symbol tilde, so xi tilde, yi tilde, which are transformed pixels. For all of the i's, for all pixels, will be the previous pixel, xi, yi location, plus that vector AB. So this is transform T. Or translation. Again, this is new pixel, location. This is old location of that pixel, and this is translation vector. Scaling of the image will be defined the following way. So let's say again that we have that image I, and we want to make that image bigger, so it will grow somehow by some scale factor, and then this pixel technically will move somewhere that direction. So this will be the original xy, and this will be the transformed xy with tildes. Formally, we can write that x tilde y tilde equals the following matrix, which is scaling matrix. S1, this is scale in the direction x, 0, 0, S2, multiplied by the original location of the vector xy. So this will be true for any pixel I in the image. In other words, it will be just S1 x I and S2 yi. And this is true basically because of the simple equations. So xi tilde equals scaling of the first location of x location, and then one is S2 yi. This is scaled second location. Just to remind you that translation was uxi equals previous xi plus a, and yi after translation was yi plus b. Now rotation is a little bit more complicated, but you get from that kind of image some sort of rotated image, and then pixel which was here move to pixel somewhere here. Clearly this should be somewhere around that picture, so it will be something like that, moving from one to another by some angle. Now, how you can actually compute the transform? First I will show you the transform and then I will prove it. So the transformed pixel is rotation matrix by angle t, which looks like that. So it's cosine minus sine, sine and cosine of angle theta multiplied by vector x, y. In other words, it's the same thing as to say system like that. xi tilde equals cosine theta multiplied by xi minus sine theta multiplied by yi, and yi tilde is sine theta multiplied by xi plus cosine theta multiplied by yi. Now, how we prove that? Before we prove it, we want to call that same rotation matrix R. So we will have basically translation, rotation, and scale. And now let's prove why this matrix is rotating one pixel into another location by angle theta. To prove how this matrix works, we need simple geometry. So let's draw the geometry of the problem. First of all, you have origin here, which is 0, 0 coordinates, and then you have x, y coordinates, which are xi, yi for a specific pixel. Technically speaking, you can find also the distance r between the origin to that point. So you can think about that as a vector, and the angle, we will say that this is angle alpha. Now, after you're rotating by angle theta, you'll get another point, which is x tilde, y tilde. Pay attention that this will have exactly the same radius, the same distance from the origin, because technically the entire motion should happen on a circle, like that. This is how pixel rotating around the origin. Now, this angle of rotation will be theta, And we definitely want to find x tilde, y tilde as a function of x, y, and theta. So this is what we are trying to do. Okay, now let's do some trigonometry. First of all, this coordinate is x. This coordinate is y. Now, from that triangle, which has those 3 points, we can say the following, that cosine alpha is x divided by r, and sine alpha is y divided by r, because this distance is x, so x divided by r is the cosine, and that side divided by r is the sine. What else we know? We can draw this coordinate here, it will be x tilde, and this coordinate here will be y tilde. Now, what we know from that bigger triangle? We know that cosine of alpha plus theta, which gives you that total angle, will be x tilde divided by r, and sine of alpha plus theta will be y tilde divided by r, from the triangle that we just drawn right now. But also, you know, trigonometric identity, that cosine of sum of 2 angles could be written as the following. So it's cosine alpha, cosine theta, minus sine alpha, sine theta. And the sine of sum could be written as sine alpha, cosine theta, plus cosine alpha, sine theta. Now, let's put definitions of cosine alpha and sine alpha inside of those 2 equations. This is what we get. We get that x tilde over r equals cosine alpha, which is x over r, multiplied by cosine theta, minus sine alpha, which is y over r, multiplied by sine theta. Second one is y tilde over r equals sine alpha, which is y over r, cosine theta, plus cosine alpha, which is x over r, multiplied by sine theta. Now, r could be cancelled everywhere, and this is what we get, that x tilde equals x cosine theta minus y sine theta, and y tilde equals y cosine theta plus x sine theta. In matrix form, it could be written like that. X tilde y tilde equals coefficients, which are cosine theta minus sine theta, sine theta, which multiplies x, and cosine theta, which multiplies y, multiplied by x, y, and this is exactly the rotation matrix that we discussed before. Now, if you want to blend rotation and scaling, we just need to multiply those matrices in a specific order. It depends if you want to do rotation first and then scaling, or scaling first and rotation. Note that generally the order is important, so it will not be the same thing to do rotation and then scaling, or to do scaling and then rotation. So we have matrix of rotation, which is cosine theta minus sine, sine and cosine, and we have scaling matrix, which is S1, 0, 0, S1, and we can multiply S and R to blend together rotation and scaling. So, for example, if you want first scaling and then rotation, and we want to apply it to vector xi, yi. Then we apply first scaling by multiplying by scaling, and then applying to the vectors that we get from that by r. So technically, the overall transform matrix will be rs, r multiplied by s. So it's just doing together scaling and then rotation. If you want to do first rotation, then this is what you need to do. First multiplying every pixel by that matrix, and then only multiplying by s. And this is the overall matrix that you get. And from that, you will get the values with tilde. So it's very convenient to just multiply matrices with the regular matrix multiplication rules. And you will get scaling and rotation together. It's very important to remember that generally SR is not equal to RS. So this one, rotation first, and this one, scaling first. Blending other transforms with translation a little bit more tricky. Since translation is not represented as matrix, it is not possible just to multiply. So what you need to do is basically to compute new values by taking, for example, rotation multiplied by xy, and then just adding that vector AB. But it's not very convenient. So the question is how to overcome that inconvenience. And for that you have interesting trick. This trick is called homogeneous coordinates. This trick is pretty simple, but tricky still. We expanding all of the coordinates with additional value. So our coordinates x tilde, y tilde will be expanded with coordinate 1 here. And regular coordinates x, y also will be expanded with 1. Actually, any pixel will be extended with just number 1 added a third dimension to those pixels. And then this trick solves the problem. Let's see how it solves it. Technically, now with that kind of coordinate system, you will be able to define translation as a matrix. And this is how you will do that. So, translation matrix will look like that. 1, 0, A. And since this is 3 points coordinates, you can do matrix 3 by 3 now. So it's 0, 1, B. And AB is still the translation vector. And 0, 0, 1. Scaling matrix, scaling transform matrix will look like that. S1, 0, 0, 0, S2, 0, 0, 0, 1. And rotation matrix, you may guess it already. It's cosine theta minus sine theta. And as always adding 0, sine theta, cosine theta, which is regular R matrix. 0 and 0, 0, 1 to make it also invertible. Now you can combine them in any order by using matrix multiplication. So if you want to do translation, you just multiply by that matrix, your x, y, 1. If you want to do scaling, you multiply by that matrix from left by x, 1 and 1 and 1, x, y, 1. And the same thing with that matrix. If you want to combine them, you just multiply those matrices together, and then you get whatever you want. Let's check some simple example. As before, in one of the examples before, we want first rotation and then translation together in that order. So let's say we have rotation by angle theta, and then translation by vector AB. So our result x tilde, y tilde, and 1. Each one of them could be index I. I'm just not using that index for simplicity. Equals. And then first you need to apply rotation. Rotation is cosine theta minus sine theta 1, sine theta, cosine theta. Sorry, here it's 0, 0, here it's 1, 0, 0, 1. You need to multiply it by xi, yi, and 1. And then you get just pure rotation. But then you also want translation, which means you need to multiply by another matrix, which is that kind of matrix. So it's 1, 0, A, 0, 1, B, 0, 0, 1. Now technically, if you multiply those two matrices, you will still get matrix which is 3 by 3. And it will include all of the information you need to rotate and translate that vector. And the matrix will be the following. It will be cosine theta minus sine theta A. Then it will be sine theta, cosine theta B, 0, 0, and 1. Multiplied by xi, yi, and 1. Pay attention that this coefficient is obtained automatically because you multiply 0 by xi, 0 by yi, and then 1 by 1. So automatically you will get that coefficient still 1, and you don't need to worry about that. All of the other coefficients are multiplied by other things, which will automatically provide the correct things here. So if you convert it to actual equations, this is what it will be. You'll have 3 values. So first of all, we multiply first row by that column. So it's xi cosine theta plus, actually minus yi sine theta plus a. So this is exactly what is expected from rotation and adding some coefficient a for translation in that direction. And then xi multiplied by sine of theta plus yi multiplied by cosine of theta and plus b as expected for the second equation. And here you get just 1. This is a solution for that problem of rotation first and then translation. The affine transform is just generalization of all of the previous transforms. So in homogeneous coordinates it will look like that. This is the affine transform matrix. It will be just having general coefficients m1, m2, m3, m4, and here the translation vector a and b, and here it's still 0, 0, 1. This is affine transform. If you apply that in regular coordinates without generalized homogeneous coordinates, it will look like that. So those transformed coordinates will be just some general 2 by 2 matrix m1, m2, m3, m4 multiplied by your previous vector plus translation. So technically you will have 4 parameters here and 2 parameters here in affine transform. Those parameters will define exactly where each point in the image will go. But it's even more interesting when you have, for example, 2 images and you know that second image is some affine transform of the first image, to find that kind of transform. So what is the transform that you have done to your image to get from one image to another? And this is very popular in the research related, for example, to panorama images, where you want to stitch panoramic images. You have separate images taken separately, and then you want to find how one image is transformed compared to another image to stitch them together in a single panoramic image. So, assuming that you have a few correspondences between different feature points, for example, you have some point here, which you know corresponds to the point here, and you have another point here, which corresponds to the point there, and then this point corresponds to this point, and so on. So when you have multiple points and multiple correspondences between those points, you want to find transform, which is in that case will be simply affine transform. So you want to find all of those parameters and all of those parameters, translation parameters and matrix parameters, which will transform from this kind of image to this kind of image. Now, in that case, those values are given because those values you find from those locations of those coordinates on the second image. Those values are given because you can define coordinates of all of those points that you have here. But you want to find this one, and you want to find this one. And it's an interesting problem how you find those coefficients if you know enough pairs of those corresponding points, which basically correspond to each other in different kind of images after rotation, scaling, and other transforms which are included in that affine transform. So this is how you do that. First, let's assume that you have that bunch of points, correspondences, and we will show them. So x1, y1 will correspond to x1 tilde, y1 tilde. x2, y2 will correspond to x2, y2 with tildes. x3, y3 will correspond to x3, y3 with tildes, and so on until you get to xn, yn corresponding to xn, yn with tildes. First question is how many points minimum we need to find 6 parameters, because clearly here you have from n1 to m4 and t1, t2 to find. So how many equations you need to find 6 parameters? Technically speaking, if you have n parameters to find, you always need at least n equations to identify those parameters. You cannot use less than n. Now, in that case, how many points we need? Because look, each one of those is 2 equations. So for a single point, we get 2 equations. So since single point gets us 2 equations and need totally 6, because we need 6 parameters to identify, it's enough to use only 3 points or more to identify all of the 6 parameters. So let's write those things explicitly. So x1 tilde equals m1 x1 plus m2 y1 plus t1. Then y2 tilde equals m1 m3 by x1 plus m4 by y1 plus t2. Now you continue with point number 2. x2 tilde equals m1 multiplied now by x2 plus m2 multiplied by y2, because this is point number 2, plus the same t1, because this is constant, this is just translation vector. y2 equals m3, it will be still x2 plus m4 y2 plus t2. And you continue with the third point, fourth point, and whatever number of correspondences you have here. Now, we can write that entire thing in matrix form. Let's see how we do that. So again, for any point I, we can write that thing as xi tilde equals m1 xi plus m2 yi plus t1, and for any other yi, we can get to m3 multiplied by xi plus m4 multiplied by yi plus t2. So those are those equations written explicitly. Now, how you write that in matrix form? First of all, we define the vector that we want to find. Let's call it vector x. So it will include all of the parameters that we want to use and to find. So it's m1, m2, m3, m4, t1, and t2. Those are 6 parameters that we want to find. Now, how we can get to the same kind of equations using matrices? So for each point I, we will have 2 lines in that matrix. The first line is xi, which is here, multiplied by m1, plus yi multiplied by m2, plus nothing else in that equation multiplies m3 or m4, and nothing multiplies t2, but the 1 multiplies t1. So this is exactly equivalent to that equation. Now, second equation will be very similar, but for the second line. So yi tilde, which is here, will be equal to z line multiplied by z column. And this is exactly that equation that we see here. Now, technically speaking, this is linear system of equations where you have many more equations, or might have many more equations than you need. So here you have at least 6 equations, because you have 6 parameters, otherwise you will not be able to solve that system. But you may have more point correspondences, so it could be at least 6, or it could be more. Now, you can call that thing A matrix, you call that x vector, and you call that b vector, and you get that system that you need to solve. Now, only if you have exactly 3 points and they are not collinear, this matrix will be invertible. Otherwise, you need more points to make the system solvable. But here you will have very long matrix like that, multiplied by some vector, so it will be n by 6, and this will be 6 by 1. So clearly the result will be n by 1, which is the vector b. Now, you cannot clearly invert matrix with that many rows, because only square matrices could be converted. So how we solve that kind of system of equations? The solution you saw already. The solution is just least squares. So you find in the closest one which will fit most of the points. So how you solve that equation where you have more rows than columns? You need to solve that thing, and in least square solution you just multiply both sides by H transpose, if you remember from the previous lectures, right? And then this matrix will be invertible. We multiply by that matrix from both sides. So this is inverse of that matrix multiplied by that matrix itself, which will give us just identity matrix, equals A transpose A inverse from the left, A transpose B. So this will be cancelled with that. It will produce I, but I multiplied by X equals to X itself. So that entire thing is actually the vector X that we wanted to find. And this is the formula of least squares that we will be using to find such a transform, which will make those correspondences as close as possible. Clearly, sometimes those points are noisy, not always you get precise correspondence, and not always it's exact affine transform, so it's approximate. So some of the points will fit, some of the points will not fit, but you are doing your best in terms of least squares solution. The last question for that lecture is how the determinant enters the picture. The answer is pretty simple. The number produced by the determinant of the transform matrix A is the image area change ratio. So what it all means? Let's try that on matrices we know now. Let's start with the matrix of translation. We know that translation clearly not changing the area, overall area of the image I. So determinant of T, which is translation matrix, is something like that. It's determinant of 1, 0, A, 0, 1, B, which is AB is translation vector, 0, 0, 1. Let's develop by the last row. This is the easiest one. So it's plus, minus, plus, minus, plus. So this one is plus. So it's plus 1, multiplied by determinant of 1, 0, 0, 1, which is giving you number 1. So determinant is 1. It means that change in the ratio is 1, so there is no change in the area. So every time you get determinant 1, no change in the area of the image. Let's try, for example, scaling. So det of S matrix. It will be S1, 0, 0, 0, S2. This is scale in Y direction. 0, 0, 0, 1. So this one, you can guess what should be the change in the area when you scaling it S1 in X direction and S2 in Y1 direction. So if your image is growing that way, for example 2 times, and that direction 3 times, clearly the area will grow 6 times. So the result should be S1 multiplied by S2. And this is exactly what you'll get from the determinant. Now, let's try rotation. As you could get, if you're rotating the image, you are not changing area of anything. You leave the same area. So let's see if it works for rotation image. This is a matrix, cosine theta minus sine theta, 0, and then sine theta, cosine theta, 0, 0, 0, 1. What is the determinant? Let's determine by the last row, for example. So it will be 1 multiplied by cosine theta multiplied by cosine theta. So this is developing by Z column. And minus sine theta multiplied by minus sine theta. So this one multiplied by this one, and the first one was this one multiplied by this one. So this is cosine square plus sine square. And from trigonometry you know that this should be equal, always for any theta it should be equal to 1. So rotation is not changing anything in the area. In general, if you want to transform which is not changing the area, which is also called area invariant, you need the determinant of the transform will be equal to 1. So area preserving transform is defined by determinant A equals 1.